So you have a small amount of this, a large amount, or sort of an equal amount. And those are sort of the three main scenarios that you deal with when you're dealing with titration. So titrations are really, even though they can feel a little bit overwhelming, they're really just an extension of neutralization reactions. Let's see, so an HCl plus a base, you'll form BCl plus, not H2, I guess because you're dealing with, yeah, I'll just leave it like that. But yeah, same thing when you're dealing with a base. I lost a proton somehow. Oh, I know what I did wrong. This should just be B minus.
Your screen is frozen. You can't see what you're currently writing.
Oh my God, dude, I'm so sorry, you guys. All right, how about now? Can you see if I scribble on here? Does that green show up? Okay, good. 2020 college, where it's just troubleshooting IT problems for the first 20 minutes of class. Okay, so anyway, so you've got basically what you're looking at is you're just looking at neutralization reactions. So if you have a base, it's the same thing. Whereas now, this is what's variable in the titration. So these things are what you're varying typically in a titration. And you're just looking at a neutralization reaction over I keep doing that. You're just looking at a neutralization reaction over like a concentration gradient for either the strong acid or the strong base, depending on what you're dealing with. Something like that. So yeah, so once you get neutralization reactions down, if you're sort of trying to just get on top of your studying, if you're behind or something, if you can master neutralization reactions, then titration should be a small step forward. If you're coming in a little bit weak on those, then titrations start to get a little bit more confusing. The curves for titration, those are unique to titrations, you know, these types of things that look like this, and sort of understanding that that's the equivalence point, et cetera. And we talked about that last class. Those are unique, but otherwise, the hard part, which is the quantitative part, just comes down to understanding these neutralization reactions. So when you're doing these, when you're trying to understand what's going on here, you can just start trying different concentrations of this relative to HA and different concentrations of this relative to B minus. And you should be able to go across sort of a whole gamut of things that you might encounter. Yeah, we'll go over indicators today. I don't know exactly what's on the practice questions, but I'll explain to you what we kind of need to see. So we'll look at polyprotic stuff and protonated states today. It's easier than you expect it to be compared to some of this other stuff we're doing. So if you're looking at, yeah, we're going to go over, I don't know about oxyacid specifically, but we're going to go over everything. Pull up some pKs here. We're going to go over polyprotics and protonation state and all this kind of stuff. I think that'll cover oxyacids. Okay, so one of the things you deal with in chemistry is, so if you're making like a buffer or you're doing something really specific, I'm trying to remember when I've done like really careful acid-base type chemistry. I think when I've done like metal analysis or something where I'm trying to figure out how much, like you're doing environmental work or something, you have to be really careful, and you have to kind of model everything using equilibrium constants. And you sort of use the same type of math that you guys have been going over. But for organic chemistry and biochemistry, a lot of times you don't really need to be hyper specific about like what's going on. You just need a general idea of what things look like. So like a more qualitative look at things. And so that's where this idea of protonation state comes from. So protonation state just refers to whether or not an acid is protonated. So if you have, let's say you have acetic acid, which is maybe one of the more common organic acids that we've dealt with, it can exist either as acetic acid or as its conjugate base. So it could be, and it's protonated, or non-protonated, unprotonated. I'm just going to non. So all you're referring to here is just that you've removed the proton from it, the hydrogen. So it can be in either one of these two states. And so what we've done sort of in gratuitous detail is look at, you know, if you wanted to calculate, for example, how much of this you have, let's say if the pH was 4, or if the pH, let's say if the pH was 4, you know, the way we could ask a quantitative problem around this would be like, at pH of 4, what is the concentration of acetate, you know, for a 1 molar solution of acetic acid, for example. You know, so we could ask you to work it out, and you could go through a Rice table and use the equilibrium constant to figure that out. More often than not, though, you're not really interested in that amount of detail. You just want a general feel for how protonated something is. It doesn't matter how exact, you don't have to be super exact. So here our pK would be equal to 4.74. So this number, the pK, is generally, if you go into biochemistry, you go into organic chemistry, that's what we work with. And it tells you the strength of an acid, essentially. So pH tells you the acidity of a solution. It's sort of independent of what acid is there, in a sense. Like, you know, the pH is literally when you go in, you take a probe. I know this can be a little bit confusing for students. So pH is whatever H plus is. So I might have a whole bunch of different acids in here, but ultimately when I put my probe in, all I'm measuring is the amount of H plus that's in solution. That's what pH is. pKa, on the other hand, which is this, that is directly related to the acid itself. So acid strength is related to pKa. That talks about like the molecular structure of an acid. So you could talk about HCl being a strong acid. You would talk about the pKa of HCl. A strong, like an acidic solution, which you could say maybe is strongly acidic or something, there you're talking about pH. So pH versus something like pKa, this is how strong is an acid. We would say, okay, it's pK, so the pK of like HCl or something might be -3 or something. Whereas when you talk about a solution, we're talking about how acidic the solution. So in this example, right, I could take acetic acid, which is this component, and I can make a really dilute solution of acetic acid. And that's what vinegar is. So if you've had salad dressing before, you've eaten acetic acid. And that's perfectly safe to eat. And I don't know what the pH of it is, but I can take this acid and I can dilute it down and safely put it in my mouth, or dump it on my hands, and it's not a big deal. People who are really into like not using store-bought cleaners like to use vinegar for everything. But this is a perfectly safe thing at the right concentration, as is something like phosphoric acid, which is in like Coca-Cola or most soft drinks, once you dilute it down, it's perfectly safe. However, if you concentrate these things, like if I take a concentrated barrel of acetic acid, so not dilute, not in water, but just perfectly pure acetic acid, it's incredibly reactive. Like if you were to get pure acetic acid on your skin, you would probably have to go to the hospital if you got enough on there. And the same is true of phosphoric acid. So concentration dictates pH, which really in that sense dictates whether or not it's safe for us to like eat or put on our skin or something. Whereas pKa indicates this other component of this, which is like how strong is the acid itself. So if you're looking at pKa for two acids that are the same, like let's say you're to draw the bridge between these two ideas of pH and pKa, if you're looking at two different acids like HCl versus acetic acid, at the same concentrations, a solution of HCl will have a lower pH. So if I take 1 molar HCl in 1 molar acetic acid, no doubt this is going to be more acidic. And here I'm referring to the acidity of the solution, so this is going to have a lower pH. Lower pH. Whereas this is going to have a higher pH, so it's not going to be as acidic. So that's the relationship between acid strength and pH. It's not like they're independent topics, but you're talking about two different things. But it's totally possible to dilute a solution of HCl down to make it weaker than a solution of acetic acid. So you can have like a 1 molar solution of acetic acid and like a 0.00001 molar solution of HCl, and the solution of HCl will be weaker in terms of its solution pH as compared to acetic acid. So if I take, just to make sure hopefully I actually get it to the point where it is, but if I take this versus 1 molar acetic acid, this is now more acidic. So now I'm referring to the pH as compared to the HCl. So acids and bases depend on, like when you're talking about pH, it's dependent on the concentration of the acid or base. Maybe that's a good way to say it. pH is dependent on the concentration, whereas pKa is an inherent property of the acid. So regardless of the amount of acid you have there, the pKa doesn't change. The pKa of acetic acid is always going to be 4.5 or whatever I said, and the pKa of HCl is always going to be -3 or something along those lines. So this is a really common point of confusion coming out of the acid-base chapter is, and if you go and read online on like a Core or one of those websites, you can see people get confused about pH and pKa being the same, and they're related, but they're not the same. So a strong acid like HCl, there is a safe, I'm not saying to go and try this experiment, but you can dilute HCl down to get it to a pH where it's safe enough to drink, for example. And conversely, if you take something that you're used to drinking, like phosphoric acid in Coca-Cola, if you concentrate that enough, it will now become not safe to drink because pH is dependent on the concentration of the acid, not just the acid's pKa. Okay, so back to this idea of protonated versus non-protonated. We started. So we dilute, let's see. So we dilute an acid, the pH will increase. Yeah, if you dilute an acid, the pH will increase because the proton concentration will go down. So as H+ goes down, pH goes up. They have this sort of weird inverse relationship. It's not that weird because it's just a logarithm, but it does get confusing to talk about sometimes. All right, so how do I know what form this is in? So I can look at my pKa, which I calculated is 4.74. So you can run through the calculations using Ka and all the stuff that we did, but a much easier way to figure it out is to just look at, you can look at the Henderson-Hasselbalch equation to figure this kind of stuff out. But if the pH is equal to the pKa, that means that HA is going to be approximately equal. Well, actually, it's going to be exactly equal. So at the, and this is something that you can look at your like a titration table or something and figure out. But like when the pH is exactly equal to the pKa, that's when HA and A minus are the same. So at a pH equal to 4.74, I expect 50% of this and 50% of this. If the pH is less than the pKa, now it's predominantly acid. So like, let's say at pH equal to, I don't know, 1, now we're going to say it's going to be about 100% acetic acid. And for the pH being greater than the pKa, now you have predominantly A minus in solution. So at a pH equal to 8, now you're going to be approximately 100% acetate. So this is sort of independent of the concentrations that you have there. There's obviously some places where this gets wonky because it's just an approximation, but it's a very good approximation. So let's come back to this one because it's a more complicated situation. But if your pH is below the pKa of your proton, so here we're talking about the pKa of this acidic proton here, or this part of the molecule. If we're below that, then we're in this fully protonated form. If the pH is above that, then you're in the non-protonated form. So when you're solving these problems, your steps should be like 1, I'm not sure, I'm trying to remember how exactly we ask these types of things, but write out the protonated and not protonated form. And then 2 is compare the pH to the pKa of the proton. And that's what this little crib sheet here is supposed to help you with. So if your pH is above the pKa, I know that I'm going to be in the non-protonated form. So if you can do this and you can do this and you have access to this in your brain or on a piece of paper or something, you can kind of work these problems. So the place that this falls out of, or one way to look at this, is you can look at, if you're trying to kind of wrap your head around why this is true, we can use this equation here. What you're thinking about is the ratio of A minus to HA. So here, this would be A minus. In this particular problem, A minus would equal this. And HA would equal this. And what we can see here, though, is that since log of 1 is 0, that's when A minus to HA is equal. So A minus and the HA concentrations, when those are equal, this number becomes 1. And when you're at equal ratios of this, so what we have written here, which is 50-50, log of 1 just goes to 0, so that's when the pH is equal to the pKa. So this result just falls directly out of just kind of understanding the Henderson-Hasselbalch equation, which is that the pH is equal to the pKa. when the concentration of an acid and its conjugate base are exactly equal. So at the pH that's equal to the pKa, we just know that we have 50-50. And then you can look, you can see what happens as you sort of change this ratio. As I start to increase, well, I guess you have to consider the pH here. But yeah, as I start to increase the pH, what do we expect to happen? Sorry, decrease the pH, what do we expect to happen? Well, if I'm making it more acidic, and I'm thinking of this in terms of Le Chatelier's principle, so I'm lowering the pH, that means I'm adding in more protons. That's going to shift this equilibrium back to the acid form. So if I add this, I'm shifting it that way. And if I raise the pH, it's the same as kind of removing protons. So now I'm going to shift the reaction back to the right. So all of these things kind of fall out of these kind of qualitative analyses. Yeah, I don't know the Henderson-Hasselbalch equation off the top of my head for the POH, but yeah, it's something like that. POH equals pKb, probably HA over A minus. I always use the pH one. Let's see. Okay. So yeah, the way these problems come up with indicators might be, let's say I have an indicator. So if you've ever used, or like, I don't know, when I was in elementary school, we did this experiment. Well, let me drink some water really quick. Actually, before I get into indicators, let's look at polyprotic things really fast. I think we can get to indicators last. Let me see. I need the pKa's. There we go. Do we want to deal with this one? So if we look at, let's say we look at I think on the GChem website, they do this with oxalic acid, which is a little bit simpler of an acid. But if you look at citric acid, which is a super common acid. So if you've, this is, in citrus fruits. But it's also, if you ever had like a sour candy or something, that coating on the outside is typically citric acid. Tastes sour like most acids. But we can see here we've got a bunch of protons. So this is an acidic proton, this is an acidic proton, this is an acidic proton. These ones that I'm highlighting in yellow, we don't have to worry about. So those are not acidic at any kind of normal pH. We're only interested in the red ones. Each of these protons will have its own pKa. So for a polyprotic acid, which is what we're looking at now, you'll have multiple different Kas for each proton that comes off. And so we can write a pKa for each of the protons here. So this one might have a pKa of, let's see, 3.13. Then this one will have a pKa, oops, of 4.76. And then this one might have a pKa of 6.40. So we have this it has 3 different protons on it. These pKa's over here are so large that they don't matter. So these protons just never come off in water. But you can look at what the protonation state of this would be. Like, let's say I'm at a pH equal to 1. All I have to do is come over and look at the molecule and say, okay, what's the pK of this proton? Or let's start with the most acidic one. So what's the pK of the most acidic proton? It's 3.13. If the pH is less than the pKa, it's in the protonated form. So let's call this, it's hard to kind of demarcate these different things. Yeah, so they're all in their protonated form. So if my pH is equal to 1, so I'm looking at a solution here. pH of the solution is 1. What's going to be the form of citric acid in here? It's going to be fully protonated. So all of my protons, I drew this in the slightly abbreviated version here, but all of these protons are still going to be on when the pH is less than the pKa. As I start to increase the pH though, so let's say now my pH is equal to 4. And let's say my pH is equal to 4. So around a pH of 4, now for some of these, like this one, it's above the pKa. So that one's going to be off. So if I redraw this molecule, so I drew it missing the carbons and stuff, which is the way we normally abbreviate these things because it makes things look clever, more or less cluttered. On an exam, we'll give you all the carbons and stuff drawn out. Okay, so at a pH of 4 though, which of these is going to be protonated? So this one has a pKa equal to 6.4. So using our little rule here, if the pH is less than the pKa, it's in the protonated form. Here our pH is less than the pKa, so it stays protonated. This one has a pH equal to 4.76. Sorry, pKa equal to 4.76. So again, and this thing gets messier the closer you get to the pH, but here our pH is still less than the pKa, so this thing's going to be predominantly protonated as well. But when we come out to the top one here, where the pKa is equal to 3.13, now our pH, now our pH is greater than the pKa, and so we would say, okay, well this thing is going to be predominantly deprotonated. It's going to be in the minus form. So even though these things look nasty, I've got this big kind of sprawling molecule, which I'm sure looks intimidating if you haven't dealt with this kind of stuff before. All you're ultimately doing is going in and looking at the numerical value for each of the protons and comparing it to the numerical value of the pH. So if the pH is greater than the pKa, this proton is not there. And if the pH is less than the pKa, then the proton is there. So if you keep raising the pH, let's see, 9:35, we got time. So if you keep raising the pH, let's say that you're now at a pH of 8, what's going to be the protonation state? Of this molecule. So those are our 3 acidic protons. But this one has a pK equal to 3.13. This one has a pKa equal to 4.76. And this one has a pKa equal to 6.40. So pH equal 8. Sorry, pH is always greater than the pKa for this one. And so the actual way it ends up looking is like this at a pH of 8. And if you keep going to pH 9, 10, it doesn't change, right? Once you've deprotonated everything, you've deprotonated everything. So that's all you have to do. All you're ultimately do, yeah, this will be on the exam. Ultimately, all you're doing is comparing the pKa and the pH. And so if the pH is less than the pKa, then it's protonated. If pH is greater than the pKa, it's deprotonated. That's ultimately all you have to do here. So a question could be, there's a bunch of different ways you can ask this question, but like the simplest way to ask it would say, we could give you this molecule here with these different pKa's and say, looking at, let's say this one here, we'll call this pK 1, 2, and 3. You know, we could say like, given the pKa's of all of these different protons here, you know, what's going to be, which of these are going to be protonated at a pH of like 2, you know? So you'd say, okay, pH equals 2. I need to take that and just compare it to my pKa's. 2 is less than 3 is less than 4.76, and it's less than 6.4. Since it's less than all the pKa's, all of these are going to be protonated. On the other end, if you said pKh is equal to 8, they're all going to be deprotonated. And then there's all the in-between cases, right? But you're just going through and you're comparing these case-wise and saying, is it protonated or is it deprotonated based on the comparison of pK and pH? pH less than the pK is protonated. pH greater than the pKa. Like deprotonated is probably the right way to say it. So those are really, I mean, you can have pH equal to pK where you're equal 50-50. That's the third one. That's 50-50 protonated, deprotonated. But regardless of how complicated your acid gets, this rule holds. Yeah, pH equal 2, everything's protonated. Perfect. So the acids can get arbitrarily complex. You can look at any acid and apply this rule and be perfectly fine. In organic chemistry, if you go and take that next semester with me, we go through and sort of explain how to approximate pKa's. So you can look at something and say, like, what's the approximate pK of this versus this versus this? You start to learn about acid strength. And I think on the GChem website, there's some of that, like what makes a strong acid, what makes us, you know, we're not going to get into that. I think that's better suited for another subject, like a different thing where you can focus more on it. Even in organic chemistry, we don't have enough time to kind of cover it all. Okay, so yeah, so indicators, the last little bit here. It's a good indicator. So if you've ever done like a pool test, I'm trying to think of where you'd use a pH indicator, or like had like a demonstration where things change color depending on pH. Sometimes in class we'll do that for this section of GChem. Obviously, I'm at my home, so we're not going to do any demonstrations, but you can find stuff online. pH indicators just tell they're one color at a particular pH and a different color at another pH. So the structures of them are reasonably complicated. So if you're looking at, let me pull one up here. Like, let's say you're looking at methyl yellow. It doesn't matter which one we're looking at. I'm just trying to give you some idea what's going on here. Methyl yellow looks like this. You're not going to have to be able to like identify these structures on an exam. I'm just trying to give you some idea of what these dye molecules look like. So when it's deprotonated, it'll look like this. And when it's protonated, look like this. Let's see, so the protonated form will be red, the deprotonated form will be yellow. Pull the pKa of methyl yellow here. Let's say its pKa is 3.5. So we could say that the pKa of this is equal to 3.5. So when we look at this, so again, I draw this big molecule not to intimidate you or like make you anxious, but like just to show that ultimately it doesn't matter how crazy the molecule looks. Ultimately, all we're considering is that proton. And so if we know that the pK of this proton is 3.5, then we can say, well, okay, at a pH equal to 2, which form is it going to be in? So pH equal to 2, or let's use, let's say even lower, like pH equal to 1. So the pH is equal to 1. The pK of the acid is equal to 3.5. So pH is less than the pKa, and so you know it's going to be protonated. Exactly, protonated. So what color is the solution going to be if you have it? It's going to be yellow. So when it's deprotonated, it's yellow. And when it's protonated, coincidentally, it's the same red I used for acid. When it's protonated, it's going to be red. I guess I can use the, oops. Yeah, so when it's protonated, it's going to be red. So what color is my solution going to be? So this one just requires like a small extra step of saying, okay, it's going to be protonated. What color is the protonated form? Oh, wait, I have it backwards. I'm sorry. Yeah, in the deprotonated form, it's yellow. Yeah, so what color is this thing going to be? Since it's going to be protonated, because the pKa is higher than the pH, then I know that the solution is going to be red. With the colors? Oh, the red-yellow thing. No, the red-yellow, the colors are dependent on the molecule itself. So some molecules go yellow to red, some molecules go like yellow to blue, some molecules go clear to purple. It just sort of depends on the properties of the molecule. So protonating the molecule changes its color. But there's a whole like mess of different colors you can have. So like litmus is the common one there. When you're in acid, it's red. When you're in base, it's blue. So the colors are specified in the problem. Colors are specific to molecule. Okay, for pH equal to, let's say 5, now our pKa doesn't change because that's a property of the acid. Now our pH is greater than the pKa. So it's going to be predominantly in a deprotonated form. And so you're going to expect the solution to be yellow. And then what happens when the pH is equal to 3.5? So that's the place where the pKa and the pH are exactly equal. And so it's going to be 50-50 protonated to deprotonated. Yeah, exactly. And so since it's 50-50 and I have both yellow and red present, yellow and red make orange. And so we perceive the solution as, yeah, I guess we could say that, yeah. So 50-50, it's an orange. This is from blending red and yellow. So, if it was like yellow and blue, then it would be green when you have 50-50. But those are your three scenarios for indicators. And typically the way we deal with this, so since this is such a messy thing to draw, and that's not really what this class is over, we'll just call it indicator. So you can abbreviate this as something like this, where it's just like indicator, and then the protonated form we can call like indicator that's protonated. So this is just shorthand for these types of things that you'll see in problems. And so in a indicator problem, colors for protonated, deprotonated forms are specified. And then you compare the pH to the pKa to figure out the predominant form. And then if you want to even call it a third step, you match the color to the predominant form. And the weird case is when the pH is equal to the pKa, it's a mix of colors. Yeah, so I don't know with the GChem website. So if you're, so at the edges, these are good questions. And this is part of the difficulty, I think, with teaching this. So I'm saying, and this is fine for our exam, I guess what I'm trying to, we're not going to give you problems where it's sort of on the border. So at the pH equal to pKa, you're 50-50 protonated to deprotonated. If your like pH is very close to the pKa, like slightly above the pKa, it's like if we look at this one, right? If our pH is 3.5 and our pKa is 3.5, then it's 50-50. If I start to raise the pH a little bit to 3.6, let's say, yeah, I'm still going to be probably having something that looks orange. I'm going to start to have more of the deprotonated form in solution, so it's going to be a little bit more yellow orange. And as I get to 3.7, it's going to be more yellow still, and 3.8, it's going to be more yellow still. And at some point, depending on the dye itself, and yeah, it probably depends on a bunch of different things, you're going to switch from being orange to just straight up yellow. I am not super worried about those borderline cases. I just want you to know that near the pH, like when you get close to the pH and the pKa, when those things are really close, it's going to be the same color. We're not going to give you one where it's like, let's say we wouldn't give you a problem where this is like pH. I guess what I'm saying is just assume that this always holds. So if the pH is less than the pKa, the pH is greater than pKa, it's fully protonated or fully deprotonated. But yes, you guys are right. There is some point at which, you won't be fully protonated. You won't be 50-50, but you'll still be able to see the other one in solution. I'm just saying, don't worry about that. If you want a metric, yeah, 0.3 is good. 1 is also good. It just sort of depends. But for us in our class, this is sort of our general rule. What happens when you get like close to, what happens when the pH gets really close to the pK, but it's not exactly equal? Yeah, things get more complicated, sure. Yeah, so on the extra practice problems, the KAs aren't necessarily on there, which kind of sucks. on those exams, I'm sure we gave it on a cover sheet. If you're the one reason we have a list of what problems don't have the KAs that you can go look them up. But if you're recognizing that you need to look them up, then you're doing pretty well, because that means that you actually understand that you need the KA to solve the problem, and that you're sort of at a dead end and they didn't give you enough information, which in some sense is harder than solving the problem. So that's really good. But yeah, we always give you the KAs if you need it. Yeah, we won't do that to you on an actual exam. How do we choose an indicator based on the pH of an acid? There are a couple of these questions on the titration homework. Good. How do we choose an indicator based on the pH of an acid? All right, so remember, if you're talking about the pH of an acidic solution, or pH of a, so when we talk about pH, right, remember, we're talking about a solution. We're not talking about a specific acid. So the question is, class is pretty much over. I need to break before I can go to office hours. But the question was, how do we choose an indicator for a specific pH? So remember, pH, we're looking at the solution. The pH is sort of ignorant of what acids are in solution. You're just sort of taking a blunt measurement of how much free H plus is in solution. So you want the indicator should have, well, it depends on how the question is set up, but it should have a pKa that is near the pH of the solution. So if you want to know what the pH, or yeah, if you want to know, like, for example, like, if you want an indicator, I'd have to look at exactly, but if you want an indicator for a solution, like, let's say pH range of 2 to 4, you might take a look at indicators with a pKa of like maybe around 3 or something. Oh yeah, sorry about the LEs getting confused. That's part of the issue of changing things mid-semester. Sometimes things get a little bit confusing. But yeah, those aren't graded. Was it LE 2.07 and 3.01 are not published, but the due date was last night, so they say they are missing. What are LEs 2.07? I'm sorry, I don't remember off the top of my head. I can go look. Give me a second. I'm going to take a break and drink some water, and then I'll be. Yes, Daniel is correct. Anything to do with solubility, equilibrium, we're gonna punt to next exam, because obviously I don't know if it's, hopefully it's not. Maybe you guys are like, this stuff's not that bad, but this stuff is usually pretty challenging. Yeah, so I don't want to overload you guys with more equilibrium crap. Solubility equilibrium will be super easy compared to the acid-base stuff, and then we'll move on to kinetics, which some students really like comparatively. Maybe they just like it because we're coming off of acid-base. But yeah, anything to do with solubility is not graded. You're welcome. Let me go and drink some water, and then I will be back in a second. I'll look at this Canvas issues. Do you guys have any specific questions? 26 and 44 on acid-base practice 1. Let's see. And 22. Okay, so we got some percent ionization question for 26. Let's see, 44. I don't know how they're estimating that thing in 44. We'll have to come back to that one. 22. 44 is estimating like it's a polyprotic acid. They're asking you to estimate how much of something is present. You probably use the Henderson-Hasselbalch equation to estimate it, is my guess. But we'll have to look at that one. Okay. Oh, practice 2. Yeah, let me get through the practice 1. So we'll do 22, 12. Okay. 12, 22. This is practice 1. I don't know if we're going to have time to do all of these. Practice 1. 12, 22, 26, and 44. And a practice 2. These are from extra. If you go in the extra documents, Daniel, there's an extra practice 1, extra practice 2. 12 on practice 1, you got that. 24. On Canvas, there should be the random problem sets. There's bound to be some weird ones in here. Exam 2, yeah, I don't know exactly how many questions it'll be. Somewhere in the range of 20 questions, 25 questions, usually what we go for. And yeah, same amount of time. We can't give more time. Well, I don't know what happened last test. For this exam, the acid-base exam, we take into consideration the fact that some of these questions are like, long to solve. So it's not going to be like 25, really intense problem solving questions. But I talked to Samoilenko about it, and both of us just felt like the time was okay. These are the exam that we gave. The last exam we gave was very similar, a little bit softer actually than the exams we typically give in class. So if you're slow on the problems, you just need to practice and get faster on them. Using the Henderson algorithm anytime we see that Ka or Kb is very small. You want to use the Henderson-Hasselbalch equation for Kf, so small Ka, Kb, and when you have Ha and A minus present. That's the key part of it. So you need to have both the conjugate acid and base present. Yeah, if you have a buffer, which is another way of saying if you have a buffer. If you look at a titration curve, if you use that as sort of your like a crib sheet for all acid-base chemistry problems, you want to use, if you're like, say you're titrating a weak acid or something, your titration curve looks like this. Your buffer, the place where you use the Henderson-Hasselbalch is in this range, and that's where you have Ha. This is where you have Ha and A minus present. So that allows you to use this buffer equation, which is this. So you can just assume anytime you're there, anytime you have both this and this present, you can use the Henderson-Hasselbalch equation. When you get close to the equivalence point, I don't know, I doubt we'll ask you something that's like right here where it's hard to say what you should or should not be using. But as you get close to the equivalence point or at the equivalence point, you can't use it anymore and you can't use it afterwards. And there's a point before where you can't use it. Like right at the beginning where you have no A minus. So if we're thinking this reaction is this. At the beginning of the reaction, you don't have any of this formed, so you can't use this equation. So like right here, if it's just like, what's the pH of a particular solution of HA? Yeah, you can't use this equation. Or I would recommend against it at least. But then as you start the reaction, so once you start adding sodium hydroxide, then you can use that. So you have to have a little bit of this present, or A minus present for this case, to use the Henderson-Hasselbalch equation. So what you're looking for Henderson-Hasselbalch equation is at the end, like at equilibrium, the question you're asking yourself at equilibrium, or maybe the right way to say it is like after neutralization. Do I have A minus, let me call them by their names. Do I have an acid base conjugate pair? If the answer is yes, you use the Henderson-Hasselbalch equation. If the answer is no, we'll just call it the Henderson equation. It's going to be something else. I know it's really confusing to figure out when the hell you're supposed to use what. And then it gets, if you start like really thinking about it as you're like, well, what about, how do I know when the cutoff is? And like when I get to this region, and I guess the answer is we try not to give you problems that are really confusing like that. We try to give you something that, you can kind of bluntly apply problem solving strategy if you can kind of figure out where you are in this neutralization reaction curve. Okay, let's get on some of these problems because we have a bunch here. I'm just going to go sequentially, even though I know you guys gave me a different order. So I'll start with 12. All right, so this one is, I'm going to, just to save time, pull up the extra practice part 1 if you're looking at it. So we're looking at problem 12, extra practice 1. So I'm not going to rewrite the question. But it asks, which equation represents Ka2 for sulfurous acid? So here you have to know what sulfurous acid is. So sulfurous acid is different from sulfuric acid. So sulfuric acid is H2SO4. Sulfurous acid is H2SO3. And so Ka1 for this is just the removal of the first proton, so the Ka value associated with that, and Ka2 is this second proton. So the proton Ka associated with that. So for polyprotic acid, each Ka, you're just removing one more proton from here. So this is sort of your bank of protons. You've got 2 of them, and you can see in this first part here, one of them has come off, and then the second part, you've got this second proton, that's the one here, that one comes off. So yeah, Ka2 is going to be, it gives you the correct answer, yeah. Let's see. Yeah, they include water with theirs, so mine's a little bit different, but hopefully that's not a mind-boggling thing. So yeah, so I've written it out sort of as shorthand here. In the actual problem, they write out water. So this would be your Ka2 equation. So if you look here, like if you get rid of water, right? If I remove H2O from this, I just have H plus left over. So it's kind of like in the shorthand, you just subtract H2O from both sides. So we call H3O plus H plus, and we just get rid of water. But yeah, that's how you work those polyprotic ones. And that we haven't focused a lot on those. But hopefully, if you're keeping up, that making this kind of jump isn't so bad. My own handwriting over here. Okay, so let's look at 22 now. Oh God, yeah, these things. Extra practice 1 is the worksheet on Canvas called Acid Base Extra Practice Part 1. Acid Base Extra Practice Part 1. Yeah, so on 22, they give you a fractional composition diagram. And it asks what the structure is of the dominant species at pH 6. I guess I'll just, we can work through this one, but just don't worry about this. 22. We may have given you an LE or something on this, but yeah, what is the structure of the dominant species at pH? And it gives you a fractional composition curve. They give you amino acid, yeah. How are you supposed to know that? I know the answer, but it's not because of what they're giving it. Though they give you, let's see, the red graph. I think something's bunk with this, messy with this problem. They have to tell you what the, yeah, I definitely don't have to, I think problem 22, they have to tell you which, do they have to tell you? I'm trying to think of how you would be able to know. Yeah, I guess I don't know. Just don't worry about 22. How about that? Yeah, the lines represent the species, and I can look at the lines and figure out which species each one represents, but I don't know that you're expected necessarily to do that. Let's just say don't worry about it for exam. I doubt we'll give you one of those. But yeah, the lines that represent it, yeah, they represent a different species, and then you look at the pH and you look at the line that's highest, and then you can say, so there it's whatever the blue line is dominating at pH 6. So the hard part, I guess, is figuring out what the blue line is. And I would know from looking at, just because of I have a, I work with this stuff, that which one that is, but I don't know that. I don't think it's fair necessarily to expect you to know that. Seems like it's more confusing than anything. All right, so 24 on practice 1, extra practice 1. This one's just asking what the hydroxide concentration is for an aqueous solution, and you've got H3O plus equal to 1 times 10 to the minus 5th. So this is a fairly straightforward problem if you know this relationship. In a solution that's made in water, the concentration of hydroxide times the concentration of the hydronium ion has to equal Kw. At constant temperature, at least, which just assume you're at normal temperatures and stuff. They don't give it to you in the problem. But if we know that H3O plus is, if we know the H3O plus concentration, then we can solve for hydroxide. So yeah, so 14 minus 5, so 1 times 10 to the 9 minus 9 ends up being the answer. So hydroxide is just this. Probably put some units on that. So you should be able to go, there's sort of like a, you should be able to go back and forth between pH and POH. And H plus and OH minus. You should be able to do this straight, like reasonably easily. So this is, you take the negative log. Yeah, I don't want to write them all out. But yeah, you should be able to jump around between these. I have a, I think one of the first videos we put on there. Yeah, we can do 49. I want to make sure I get to 26. There's a video for how to do this. I don't think I'm not like, I don't set up the strategy perfectly, but I worked through a bunch of problems with it. So hopefully you get I worked through 2 problems with it. So hopefully you get a good feeling for it. But there's equations that can take you in either direction here that are pretty simple equations. So you don't want to miss points for that. All right, so 24. But, oh no, I see. That's okay. I got screwed up there and did practice 2. I'm surprised that came up. Okay, yeah, 26. This makes more sense. So in problem 26, extra practice part 1, we're looking at a generic weak acid that has a percent ionization equal to 10.8%. It's at 0.025 molar concentration. What is the Ka of this acid? So for me, if I'm dealing with equilibrium constants, I start out writing whatever the equilibrium reaction is. And so they're asking for what Ka is. So you know that in order to solve this, you're going to need the concentrations at equilibrium. So ordinarily, the way that we ask these questions, we'll ask you what the concentration is. We'll say like, what's the pH, or like what's A minus at equilibrium. Here, they're kind of giving you the opposite. They're saying, they're indirectly telling you what the equilibrium concentrations are, and you're calculating Ka from that. So the weird thing, or the hard part here, is that they're saying we've got a 0. We can write it out in the Rice table. They're saying we start with a 0.025 molar solution, and all they're giving us, they're saying the percent ionization is 10.8%. Sorry, that was looking weird to me. Let me just write it. So 10.8% ionization. So percent ionization is gives you a pretty straightforward handle on what the equilibrium concentrations are going to be, because it basically tells you at equilibrium 10.8% of this is going to be dissociated. So that means that you can subtract away 10.8% from this, and that 10.8% doesn't disappear naturally. It appears over here on this side of the equation as protons and A minus. So Yeah, so we want to subtract out 10.8% of 0.025. So that's going to be 10.8. Actually, that's going to be minus 0.0027. So I'm taking 0.025. I'm saying I know 10.8% of it's getting ionized. So that's going to be, we want to convert 10.8 out of percentages. And that's going to give me 0.0027. And this is the amount of this, the starting concentration that is no longer there at equilibrium. So you lose 0.0027 of that. And that means that at equilibrium, Z, we're going to have gained that much of these on the other side. On our way to equilibrium, I guess, since we're looking at the change part. But at equilibrium, it's going to be the same number. And then whatever this is. And then we just plug those values in over here. Come out with some number, 3.3 times 10 to the minus 4. What I come up with. Yeah, that's what they come up with too. But yeah, so the key is recognizing that. So for these questions where they ask about the percent ionization, the key is recognizing that that tells you, unlike, so normally when we're solving these, right, we're plugging in values for X and we have Ka. So usually we're given Ka and we have to solve for some other unknown. In this problem, we're not given Ka, we're given this number. And the key to recognizing how to solve this problem is recognizing that this 10.8% ionization tells you the equilibrium concentrations of everything. It says that at equilibrium, whatever I started with of HA, I'm going to have lost 10.8% of it, and that the products, I'll have gained 10.8% of those. So at equilibrium, I'll have lost 10.8%. Let's just call it 11%. I'll have lost 11% of my HA, and I'll have gained 11% on the product side. And then I can take those values and plug them in here to get my equilibrium constant. Okay, so 44 on the extra practice, part 1. It's asking about phosphoric acid. So it's saying that we have H3PO4, and that's at 0.01 molar. And it's telling us that pH for the solution is equal to 2.24. It's saying estimate the concentration of phosphate, which remember is this, in the solution. And then it gives you values here. Ka1 is equal to 7.6 times 10 to the minus 3. Ka2 is equal to 6.2 times 10 to the minus 8. And Ka3 is equal to 2.1 times 10 to the minus 13. So what they're referring to here is that's going to be Ka1. So all you're doing when you're looking at different Kas is you're removing successive protons from a polyprotic acid. That's going to be Ka2. What am I doing here? So if this is confusing you, here's my acid, here's my conjugate base, and you can see that the conjugate base then enters into the next Ka value. So I take the conjugate base, and now it behaves as an acid in this equation. And then you take its conjugate base, and that goes into the next equation and loses a proton. And then we see its final deprotonation status to form phosphate. It's lost all of its protons. So at pH 2.24, the easiest way to kind of look at this is probably to look at the pKa values. And use that trick we talked about in class today. So pKa1, pKa2, and pKa3. pK1 is 2.1. pK2 is 7.2. pK3 is 12. Close enough, 12.7. So then I just take this and I use that little metric from class today. So it's asking for, so hold on, I forgot what the problem was asking for. Estimate the concentration of PO4 minus 3, yeah, okay. All right, I remember this one because I said I don't know exactly how to do this. But so let's look at our pH. So our pH is 2.24. Our pKa values, if we look over here, so our pH is much less than pKa1, pKa2, and pKa3. So I'm not expecting, let's see, I'm expecting most of this thing to be, most of this to be protonated. How are they figuring this out? Let me see. I know it's going to be a really small number. That's not what they're at. Yeah, I took the negative log. Let's see. I think you just use the Henderson-Hasselbalch equation. So for the most part, when you're dealing with Ka values, let's see. I'm trying to think of like how to explain what my thinking is, why this is valid. Oh no, because you're looking at phosphate. Let's see. I'm not sure exactly how they want you to estimate this. Small. It's like clearly not close enough to what they're saying. You did 3 rice tables. Yeah, that's one way to do it. I feel like there must be an easier way to do it though, but it wasn't getting the right answer. Damn, that sucks. Yeah, I mean, the one way to do it is to figure out, the longhand way to do it is to like calculate how much H2PO4 you'll have at pH of 2.24 for this first one. and then take this value, let's see, and you could plug it in here, and then calculate how much of this you'd form. And then you could take that value and plug it in here and see how much of that you form. I doubt we'll give you a problem like this on the exam. So we can skip this if you guys aren't interested in working it out. It's an interesting problem, though. I'm not totally sure. There's got to be a certain short hit, like a shortcut here. I feel like I'm missing that doesn't require multiple Rice tables. I feel like that's just kind of barbaric for an exam. Oh yeah, you have to plug in the pH for the Rice table. So whatever the pH is tells you your H plus concentration over here. So plug that value in. So if you're using Rice tables to solve this problem, make sure that you take this pH value and use it to calculate whatever this is. So that's going to be the starting concentration. This is the inverse of the pH to make sure that that's in the right units. And then 0.01. So you could say minus X, plus X, plus X. There's got to be a way to use the Henderson-Hasselbalch equation here. I feel like that's what they're trying to get you to do. Let's see. We know the pH, we know the pKa. I guess that's a way to do it. So you could say, I guess you could say, I don't know how much faster this really is, but you could say, so we know the pH is equal to the pKa. Let's say pK1 plus log of H2PO4 minus over H3PO4. And so you could solve for this from that equation. Actually, that's it. I'm just a dunce. All right, here we go. Is that true? Yeah, I think you can just say, here's what you do. We can say that the pH is equal to the pKa3 plus the log of their phosphate It's like, man, the expectation that you'll do this is kind of outrageous. But this allows you to calculate it. So we know the pH and we know pKa3 because I calculated it already. And then we can calculate the ratio of these two things over here. So we could say, let's see, the pH minus the pKa3, and we want to take inverse of that log, so that's 10 is equal to PO4 minus 3 over HPO4 minus 2. This has got to, I feel like we're close at least. So 10 to the pH minus the pK, so 2.24 minus 12.7. That gives us our ratio of those two things together. That means for every one HPO4 minus 2 we have, we'll end up with 3.47 times 10 to the minus 11th phosphates. Oh, we're so close. So the place I'm stuck at is this equation is valid, but doesn't give me the concentrations. It gives me the ratio of the concentrations. And so in order to solve this, I guess we need to know what our concentration of HPO4 minus 2 is. So I guess you would need to go back. Let me calculate this exactly. Oh, God. I really want to solve this problem, but I want to get through the other ones. Yeah. Ka1 is definitely really large relative to the other ones. So H plus concentration should be the same as phosphoric concentration, the first concentration. It's not that large, though. Yeah, sorry. Yeah, so sure. It won't be on the exam. How about that? Let's see. So Ka1, yeah, so Harleen, the Ka1 is large, but in order for you to say that H plus and H, I like the way you're thinking, but in order for you to say that H plus should be the same as H3PO4, it has to be greater than 1. So it's large relative to the other ones, but it has to be greater than 1. It's still much less than 1. So it has to be like 10 or something. Ah, damn it, this is aggravating me. All right, well, I want to solve this problem, but I don't think you guys really care if it's not going to be an exam. So let's skip ahead. Yeah, that one's interesting. So yeah, if you want to do it, if you really want to punish yourself, you can go through and do it with Rice tables. There's got to be some shortcut using the Henderson-Hasselbalch equation that I'm just missing though. I'm sure it'll hit me after office hours end. All right, 44 and then 49. So 44. So like, let's not worry about this one for exam. I keep getting drawn back into it. All right, no, don't think about it. All right. All right, so 49. Oh, good, something qualitative. All right, so 49 is, it asks which of the following aqueous solution gives a pH greater than 7? And then it gives you a list of things. It says 10 to the minus 8 molar this, 10 to the minus 8 molar this. Basically none of the above. So this is just being able to identify acids and bases. So if we look at these, it's hard because it's like, for me, it's like this is an acidic proton, that's an acidic proton. Ammonium is acidic, it's NH4 plus. It's equivalent to saying NH4 plus, so it's the protonated version of the amine or ammonia or whatever. And then this is also acidic, that proton. These are all acids. So pH is going to be less than 1. So, you know, if you had something in there like hydroxide or ammonia, not ammonium, you would expect a pH greater than 7. Yeah, H3PO for the last question, H3PO4 is a weak acid. I don't think we'll do anything. I don't know what the specific question is, but probably not. Probably no charge balance equations. Like asking you like, yeah, like if you have like a -2 on one side and -1 on the other, what's the stoichiometry for that or something? We probably won't worry about that. Oh, like what is charge balance? I don't know without seeing a specific question, but charge balance just says that whatever the left hand, whatever the, and I kind of break this rule all the time because I write everything shorthand, but charge balance just says, like if I have, like you'll see me write out this. So this equation is charge balanced because the sum of the charges on this side, -1 + 1, is 0. And the sum of the charges on this side, which is just 0, is 0. That's what charge balance is. Yeah, I'd have to look at the specific question, but that's usually when people are talking about charge balance. It's just that the sum of the charges on the left and right hand of the equation should be equal. Back too far. Okay, let's go to practice 2. Are there any more in practice 1? All right, so we're looking at problem 24. Extra practice part 2. Problem 24. Okay, here we go. Oh God. Okay. Some of these problems they come up with. Someone's asking about RNA and stuff, but you know the problems are fair as long as they should hold to the basic premise of the. Okay, so it's a bunch of useless crap information, but the basic question is, so it says lithium acetate is a common component of the buffer system used in gel electrophoresis of DNA and RNA. So this is where this stuff gets used a lot, is in biology. And it says, how many moles of lithium hydroxide do you need to add to 650 milliliters of acetic acid solution to make a buffer with a pH of 5? So let's take a look at that. So it says, they're asking how many moles of lithium hydroxide. And we have a 650 milliliter solution. Of acetic acid. .59 molar. And then we want the pH equal to 5. So this is, in spite of the way that we kind of teach it, this is like kind of the more likely way that you encounter acid-base chemistry if you go and do lab work, is you're trying to make a buffer. So we're trying to make a buffer and we want it with a particular pH. And so there's a bunch of different, practically how you do this in the lab is you would get 0.59 molar acetic acid, and you would put it into a flask. And then you would titrate in essentially lithium hydroxide until you hit the pH that you want. This is asking if you have a standardized amount of lithium hydroxide, how much you're going to add. Let me write it out in chemical form. So they're saying in this reaction, this is essentially the reaction you're looking at. What you need to know to solve this, so sort of what you're starting with here. So remember, for neutralization reactions, we always back out into moles and we don't work in concentrations. So your first step is going to be to calculate the number of moles you have there. So that's going to be 0.59 times 0.650. So we have 0.3835 moles of this. What you're trying to figure out is how much of this do we need to form, because we're trying to make a buffer, in order to have the pH equal to 5. So at some ratio of CH3COO minus, the lithium is kind of irrelevant, but I'm going to write it anyway. Some ratio of this to this, the pH equals 5. So that's sort of the first thing you're trying to figure out is like, what is this ratio here? And we can figure that out using the Henderson-Hasselbalch equation. So pH is equal to the pKa plus the log of this over this. So the pK, so what they should give you in this problem, which they didn't, is that the Ka of acetic acid is equal to 1.8 times 10 to the minus 5th. And I know from the last problem we worked that this works out to be a pK of 4.74. Let me double check that. So on an exam, we would give you that. So this is the Ka associated with this reaction. And so we're trying to find, what we're trying to find is the ratio of this to this. That's what we have written down here. And so we'd say, well, at a pH of 5, we can rearrange this equation actually before we get going and plugging in values. So if we plug in the values for the pH and the pKa right here, raise them to the power of the 10 to get rid of the log, it'll give us the ratio of these two components in solution that we need. And so 10 to the 5 minus 4.74 equals 1.8. Do that right? That's up here. What is this? 24. Trying to read their answer for it, and that's even confusing there. Because the buffer equation. Oh, the right prime, no, that's 26. Okay. I was like, damn, I really don't know what's going on. 24. There we go. Okay. Yes, I am working out properly. Okay, good. I just wanted to check. I was looking at the wrong problem, and I was like, man, I'm way off. All right. Yeah, so this gives you the ratio of your conjugate base to acid that you need in solution. Yeah, maybe this will give me a hint on how to do the problem that I couldn't solve the other one. Okay, yeah, so then we can come back up here. So we have 0.3835 moles of acetic acid. This is just a ratio. This is where I was running problems in the other one. This is just a ratio here. It just tells you that for every 1.8 of these, you need 1 of these. So it doesn't tell you the concentration. So you need to take the number of moles that we originally calculated here and use that. So 1.8 is equal to 0.3835. Let's just call that 38. So that's the moles of, this is the moles of acetic acid that we're starting with. There's nothing magical about the number. It's just how much we literally have. And then we're trying to solve for, like, let's just call it X, how many moles of lithium acetate we need. And we know that the ratio that should hold is 1.8 to 1. So we can just solve that. So yeah, if we want to be really careful with our units here. Just to make this a little bit more obvious. Once we work this all out, what you should end up with is this thing equaling 0.38 times 1.8 mole.
So we're allowed to just put in moles and not concentration for that?
Yeah, I kind of skirted this. Maybe it was in office hours or maybe it was in class. So for the Henderson-Hasselbalch equation, just to simplify things for students, I said just always work in concentration here. But for the Henderson-Hasselbalch equation, if you think about it, since they're in the same flask, the volume component always kind of cancels out. So the moles should always work. So it's like if you think about it like this, like this is going to be equal to some amount of moles in 0.6, I think it's 6.5 liters. And then the concentration of acetic acid is also going to be equal, it's going to be equal to 0.38 moles per 0.65 liters. And so even though you're not using molarity, if you plug these into a ratio, let's say you divide these two concentrations by one another, what we see is it doesn't really matter because the concentrations are the same. So this ends up canceling with this. And so it becomes X over 0.38 moles. So you don't have to, for the Henderson-Hasselbalch equation, you don't have to know the volume necessarily. You just have to know the ratio of the moles. But for simplicity's sake, I just say always back out in the concentration, just because that is generally a good idea.
Okay.
Yeah, it's because they share, it's because they're in the same flask, the volume's always going to be the same. But yeah, that's the part that was getting you, that's all it is. So yeah, so then you want to go back. So now that we know it should be 0.68, you know that at the end of this, you want to have hold on, I might have messed up something there. I'm going to calculate the mole fraction, not just simply the. Let me think for a second. X. Yeah, hold on. That's all true, but let's see. I think here is where I kind of made a wrong turn. Slight modification. Yeah, so it's not, so you're not, since we're building the buffer in this way, the way I calculated it is if you're, it's as if you're adding, like my mistake was I calculated it as if you're adding in this much, but you have a set amount that you're starting with. So you want to say, let's see, so you're looking at, yeah, these things are tied together. That's my mistake. So you're looking at the moles. So if this is equal to X, then the amount that X is the amount of acid that you'll lose. So you'll lose that much from here. So you know, so one way to set this up, one way to think about it is to say, that's going to be plus X at the end. So we're just saying that whatever amount of acetate, lithium acetate that we form over here is going to have to come from the acetic acid that we started with. That I kind of gaffed on that a little bit. But we can represent that by saying, okay, well, the change in moles of acetic acid is going to be 0.38 minus some amount X. And the amount of lithium acetate that we gain is going to be equal to X. And then it's just a matter of solving for X. So shortcut, say solve for X. That'll be 10 to the whatever. So X will end up equaling 0.247 moles. Let me think for a second. Okay. All right, yeah, it's most of the way there. I gapped on this part. All right, so let me take it from the top. So you start out, so they're asking you how many moles of lithium hydroxide you need to add. And what you're really trying to figure out is at what is the concentration of acetic acid and lithium acetate at pH 5, because that's going to be your buffer. So for a buffer that has, for a solution at pH 5, you know, how much of this acetic acid that we're starting with, 0.5 nomolar, has to be lithium acetate, converted to lithium acetate? That's sort of the question that we're asking. And so we start by taking the Henderson-Hausbach equation and setting the pH equal to 5. And then that allows us to calculate this ratio that for a pH of 5, regardless of the concentrations, so this is concentration independent, the ratio of lithium acetate to acetic acid should be 1.8. So once we have that in hand, we have to go and actually work with a real concentration here. So we started out with 650 milliliters of 0.59 molar acetic acid, and we calculated that that means we start out with 0.3835 moles of acetic acid. And so we can work with moles here for the reasons that we talked about, where the volumes cancel out. And so we set up a new equation here where we say, okay, let's see, say at a pH, actually, I think we don't even need the Henderson-Hasselbalch equation here. We just know that this holds true. Yeah, there we go. So then we just say, okay, we know that the ratio of lithium acetate to acetic acid is going to be 1.82. And then we know that these two things are tied together. So some amount of acetic acid is going to get lost, and we're going to call that X, and then whatever amount gets lost we're going to pick up as X. And so that's what we end up solving. So we say 1.82 is equal to X over 0.38 minus X. And that's how you end up solving this for X. So you end up with X equals 0.2475 moles of lithium hydroxide. I'm trying to work that too fast and get messy. But the workflow is, let's see, so one, it's figure out molar ratio of the conjugate acid, let's just call it A minus, conjugate base A minus to HA at the pH. And then step 2 is use that ratio to solve for the actual. So actual meaning like, so this, what you're solving here is, it's just a ratio. It's a pure number, so it doesn't have anything concentration units associated with. So you're going to use that ratio to solve for the actual concentration, or in this case, moles.
The PK would be given to us, right? Or the Ka?
Yeah. So generally you're given the Ka. I just do it. I've worked acetic acid, so I know that one by heart. So, but yeah, that's basically the workflow for that one. It's weird. It's the way that you work with acid bases in the lab is so different from the way that we teach it. Not that it isn't valuable to go through this stuff, but usually when you prep a buffer, you have a pH meter, so you're doing this sort of inverts the way the lab work typically goes. But yeah, this is a way to do it. Maybe this is how biologists do it. Maybe lithium acetate or lithium hydroxide or something isn't hydroscopic. I don't know. But yeah, this is how you do it. 38 minus X. Yeah.
When is exam 2 gonna be? Or like what time?
It's at the same time as exam 1.
Okay.
Everything is basically the same, yeah. Same time, same amount of time, etc. Same rules. Yeah.
Okay.
All right. Good luck with your study, and I'll see you guys on Wednesday morning. And yeah, just try to stay calm while you're studying this stuff. It's pretty hard, so don't get discouraged if you're struggling a little bit.
Have a good day.
You too.